All right. Hi, everyone. We're getting started actually only 1 minute late. That's great. So what I hear about what just happened, there are lots of wet labs in this building in the sense that they work with chemicals. And anytime anything is spilled whatsoever, they have to pull the fire alarm and call the fire department. They're normally super careful about these things, so the fact that they've already left means it was probably water or something. Yeah, the reason I was gone for a couple minutes there, grabbed another lecture hall in another building, came back, and this was all clear, so great. Looks like we didn't even scare that many people away, so this is perfect. Yeah, so let's just get started on the announcements. Project One Search was released last week. It's due Friday at 5 p.m. As a reminder, you can do it solo or in a group of 2. Super important. If you do it with a partner, both of you submit your code separately. If one of you doesn't submit, then the one who didn't submit will not get credit on edX for it. Project One mini contest, that was just released in the last half hour or so. The idea here is it's for extra credit and for glory. It's Pacman, except instead of Pacman against the AI ghosts, you have your AI playing Pacman, an opponent's AI also playing Pacman, and you're trying to capture all the dots on the other person's side of the board before they can. It's like Pacman capture the flag. We're going to iterate on this contest throughout the semester and add more rules, make it a little more complicated. After we cover adversarial search, which is today, for contest 2, we'll be able to add adversarial behavior, where your Pacman are not just racing to get all the dots anymore, but also trying to defend your own dots and predict what the opponent's Pacman will do. If you'd like to participate, and I strongly encourage it because it's not worth a ton of extra credit, but if you participate, it's highly likely that you'll end up in the top 10. So there's a good chance for a small amount of extra credit. So even if you're not going for the glory, there are some incentives there to participate. It's pretty fun too. If you want to participate, the instructions for sign up are on Piazza, and the rules for the game are on edX. Homework 1, which is, got those headings wrong. But yeah, homework 1 is search and CSPs, and that's due Wednesday. Sorry to frighten all of you who thought it was due today because I had that on the board while I was talking. Sorry about that. This is what this should say. Homework 1, and that shouldn't be in red, but whatever. Due Wednesday. And then office hours. I've been mentioning office hours in the context of homework all of last week. As a reminder, you can come into office hours for any reason. If you're struggling with some conceptual concept, if you want help on the contest even, yeah, homework help, project help, anything in the course. It's not just for homework. But yeah, today I'm not going to be able to stick around like I was last week. I have somewhere to be right after lecture. But fortunately, now we have a regular office hour schedule that you can see on Piazza. Yeah, question?
Can we extend the mini contest to Monday because it's a holiday?
The holiday is Monday, right?
Yes.
Yeah, the reasoning for the deadline being set on Sunday is because we don't want to have a deadline on the holiday, because then it's like, forcing you to work on the holiday. It's extra credit, but still, we're trying to avoid that. So we're going to leave it on Sunday. Any other questions about logistics? Great, let's get started. So, like I hinted at earlier, today we're talking about adversarial search. And the context that we're going to be talking about this in is playing games. Pacman is the example we've seen a bunch of times. We're going to talk about some other games too, and how, in general, we write AIs to play games well. So let's look at the state of the art. You'll notice as we go through this that there's some new information on this since the last few times CS188 was offered. But the first game that AIs were really playing, and we saw this in the first lecture in that video, was checkers, where they were, for the first time, trying to reason like humans were. This was back in 1950. It wasn't until 1994 that we actually had a checker playing AI that measured up to human experts. And we had Marion Tinsley, who was, how long was that? 40-year reign as checkers world champion. No one even came close to him. Blew every other human player out of the water. And along comes Chinook, this AI that plays checkers, and beat him. First player to beat Marion Tinsley ever. And so in 2007, checkers was solved. And we'll be able to say more concretely what I mean by solved by the end of this lecture. But the point is, it's not possible to do any better than what we currently have AIs to do. They play checkers perfectly. And so that's where that is checkers, if you have an AI to help you play it, you might as well not play the game anymore. It's tic-tac-toe. We talked about chess, also in the first lecture. There was this historical moment in 1997 where Deep Blue was the first chess program to beat a chess champion. And we talked about how that was going to work. It basically searches down a whole bunch of different trajectories of how the game could run, evaluates how well each one of those is going to turn out for the AI player, for Deep Blue, and then chooses which way to go based on that. And we see, well, I don't have my pointer on right now, but 200 million positions per second. That was a lot back then. That was running on supercomputers. Now you could run that on just your laptop, probably, if you have a nice laptop. And so chess is not solved in the way that checkers is. It's still theoretically possible to play better than Deep Blue and our even more current state-of-the-art chess engines. But it's significantly better than expert human level at this point. And then Go, which was considered the final frontier for AI game playing for a long time. The reason it's so much harder, as we talked about, is there are so many more moves at every turn that you could take, different ways the game could go, and you need to be able to plan very far ahead, just like in chess. Only now it's way more expensive to plan that far ahead. Recently, in March of this year, AlphaGo, which was from Google DeepMind, beat a human champion. There's not a reigning world champion in Go as much as there was in chess, least at all, but this was the first time that an achievement anywhere near that level had been reached by an AI in Go. And so we used to have the Go up above human level, but not quite at expert level. But now Go is about on the same footing as chess. And then, of course, what you're definitely wondering is Pacman, because that's what the game that we care about. So Pacman has not been as rigorously analyzed, how well it measures up to the best human players in the world. We're going to try to figure that out today. What we want to be thinking about in general in AI, and especially today, is how to write programs where from computation there emerges behavior like how we expect it should be played, the game should be played, but without explicitly hard coding those behaviors. So for example, if we're playing Pacman, we say, we don't want Pacman to go into a dead end. We don't want Pacman to run into a ghost. We want Pacman to eat the dots, and so just have a bunch of if statements. If there's a dot in front of me, step that way. If there's a ghost that way, step the other way. These kinds of things, they're very brittle. There's all sorts of exceptions, and it's not going to handle the situation where all of these things are happening at once and you need to reason about which of those if statements should take the most precedence, all these kinds of things. And so we are working on algorithms that will work generally, that will, based on the rules and the formalism of the game that we give it, figure out how to play it as well as it can. So I want you to think about how we might do that as we watch this video. Yeah?
For the competition, do we have to start it through Python, or do we use a different engine?
It has to be through Python, because we're directly evaluating your code on the server.
Wait, can we turn it into separate codes? One for competition, one for evaluation?
One for the contest, you turn in one Python file. So unfortunately, I was having some graphics bugs running this code on my computer, so we're going to watch a video of it running on someone else's computer. But think about what kind of reasoning we'd have to be doing for this behavior to emerge. He's playing pretty well. avoiding the ghosts except when they're scared, getting them when they are, and eating all the dots. So we're going to get into what's slightly different about this than what we were doing last week, which is now we have to predict what an opponent who is trying to make us lose is going to do. We don't have a straightforward, if I step to the right, then the environment will be in this new state, because there is someone else making decisions at every step along the way. And so we have to figure out how we can model that and then reason about how to work with that. Adversarial games, as it's called. So you'll notice that games, as we mean it when we just say it colloquially, we're talking about video games, board games, all sorts of different games. There's a very specific type of game that I've been addressing here right now. So thinking about checkers, chess, and Go, deterministic versus stochastic, or are there randomized elements of the game? Which of those categories do those three games fit in, deterministic or stochastic? I hear deterministic. Raise hands for deterministic. Okay, we got about half of everyone. Is everyone else stochastic or just abstaining? Abstaining, okay. Well, yes, it's deterministic, and that's because when you choose that you want to move your checker piece forward to the square, there's no probability your move might fail and it doesn't get there or anything like that. As far as your moves are concerned, you know exactly what the result's going to be. There's no random elements of any of these games. So that's what we're talking about today, deterministic games. Zero-sum is a concept we'll come back to in a minute. That's not as straightforward. Will take a little bit of effort to wrap your mind around. But these games that we're talking about today are also zero-sum. What about perfect information? So you can see the whole board in all of these games. So they're perfect information games. Can someone give me an example of a game that is not perfect information? Yeah. Any MOBA. Yeah, so a lot of video games where you can only see part of the environment, your screen covers maybe 1/10 of the area where there's action happening, you have to walk around and gather information about what's going on so that your screen covers more of the board. We're not talking about those games today either. For now, you know the entire configuration of the game. And we're trying to come up with an algorithm that will compute a strategy, policy, which recommends a move from each state. Now, notice that this is slightly different from before. We wanted a plan, which is a path of execution from my start state to a goal state. Now it's a policy, which is you're going to have to keep evaluating it over and over. I'm right here. This is the best move I can take. Then something happens that's out of your control. So now you don't know after that, after your opponent moves, what the resulting state will be. So you need to be able to account for all of those different contingencies. So we're trying to come up with a strategy, not just a plan. So here's our model for deterministic games. And unlike some of the formalisms we saw last week with search problems and CSPs, it's not quite as, there's not as much of a consensus about how to model this. But this is the one we're going to go with, where you have states, similar to the search problem, only now your state probably has a little more information about where your opponent is, but nothing really different there. Players, a number of players. In Pacman, there's going to be Pacman and then 2, 3, 4 ghosts or so. So 3 to 5 players. Actions, and the action space for different players might be different. In Pacman, it's not. They can all just move in any direction. Transition function works exactly the same as with the search problem. And terminal test, again, same as with the search problem. We need to know for any state, has the game ended if we find ourselves in this state? And finally, terminal utilities. This is slightly different. Where in a search problem, our goal was just to find a state that was a goal state. Now, we know eventually we're going to end up at the end of the game. We want to have a favorable ending. So in the case of these games that we talked about, how about chess? Favorable ending means you win. So we can say the utility for winning would be 1. And an unfavorable outcome would be you losing. The utility for that would be -1. And then you can also tie. So that would be 0. We'll see a lot more examples of how to assign utilities to nodes. But what's important on this slide is that for our model of how a game works, the terminal utilities are part of the game itself, not part of the algorithm that we have to come up with. And so for most of these games that we're talking about today, it's going to work like I said, where you get some positive score for winning, some negative score for losing, and 0 for draw. There might be other games, like you see, well, oh, sorry, that's Pacman. But if you were playing a slot machine or something like that, that's a one-player game. So not the greatest example, but the point is there are all sorts of different outcomes that have different amounts of positive or negative utility for the player. So that's going to be something predefined for us. Yes, question?
Is the R in terminal utilities, is that R, is that a real number?
Yes, the R is going to be a real number. Good question. Yeah, it's not, yeah, it's Blackboard R, you know, real numbers. And then, like we said last slide, the solution is a policy, not a plan. So zero-sum games, I mentioned this phrase. You may have heard this before, but the idea is in a zero-sum game, the agents have opposite utilities. Think about it. If I said that for chess, 1 is win, -1 is lose, then that means if I win, I get 1 utility, and the opponent gets -1 utility. Or in the case of a draw, we both get 0. In all of those cases, the utility, my utility plus my opponent's utility is going to be 0. The reason this is useful is, well, A, this is a model that applies to a lot of games that we actually care about, especially if there's any notion of a winner and a loser, then it's usually going to be a zero-sum game. And what this allows us to do is rather than keep track of our utility when we're simulating what moves we'll want to take and our opponent's utility when we're simulating what moves they want to take and try to maximize 2 different numbers, we can say there's one number, my utility, and I'm trying to maximize it while my opponent tries to minimize it. Because a really good score for my opponent would be if I got -8, something like that. So that's why we care about zero-sum games. And a quick nod to general games, which we'll talk more about tomorrow, is where this is not the case. So here, the 2 robots are fighting over 1 gem. One of them is going to get it, the other is not. In the general games case, they're both trying to maximize something that doesn't necessarily conflict with each other. So the blue robot's grabbing the green gems, the red robot's grabbing the red gems. And what's very interesting about this is that behaviors of cooperation, indifference, and competition can all arise. Again, this is something we'll see more tomorrow, but like I said, we're not explicitly coding in most of these behaviors, but these will arise just from the computations of simulating what the opponent's going to do to maximize their score and doing whatever we need to do in response to that to maximize our score. Sometimes we cooperate, sometimes we compete, and sometimes we just ignore them. So adversarial, yeah, question?
Can you have a zero-sum game for more than 2 players? Or is that...
Yes, you can have a zero-sum game for more than 2 players, but then you don't run into the super useful property that the opponent's utility is just the negation of ours. Pacman actually is an example where it's a little interesting because we have Pacman's utility and the ghost's utility. They're all on one team. So they're acting as separate agents, but they're all getting the same exact score. So in that case, actually, it's more than 2 players, zero-sum, and there's only one number that Pacman's trying to maximize, and all of the ghosts together are trying to minimize. We'll talk about that a little more later, too. Good question. So what's happening in this picture? We're imagining what the opponent's going to do, and we want to account for all possible outcomes. So what we're going to reason about right now is our worst case outcome. What can we guarantee that we can do? And when is the worst case outcome going to happen? If the opponent is also playing optimally. So we're imagining that they are, in turn, simulating us, and now we have this mutual recursion. And here, we're going up in thought bubbles. In a minute, we're going to see trees, where this guy's the root of the tree, and all of the red guys he could imagine are the next level of the tree, etc. So first, before we get to that, let's think about what that would look like for a single agent. And this is going to look a lot like a search tree. The only difference is now instead of goal states and non-goal states, we have a whole bunch of terminal states, and they have different values assigned to them. So all of the successors of this are going to get expanded out, which is Pacman can go left or right. And then When we go one level deeper in that, Pacman can again go left or right, and we have all of these. We're not going to go through the whole tree, but just imagine for now, this one on the right is a terminal state, but imagine we go all the way to the bottom on those other branches, and we have to assign values to all of these. So, reminder, in Pacman, every time step you get -1 point, and for eating a pellet, you get 10 points. So, the score on this rightmost branch is going to be 8. Before I add all the other scores, keep in mind that this is slightly different for another reason from search, where before we were trying to minimize a cost, today we're talking about maximizing a value. Keep that in mind. No longer minimizing, now we're maximizing. And just say, if we follow these all the way to the bottom of the tree, those are all of the final outcomes we reach. Those are the scores attached to them. So, what would we do? If we know this is the search tree, how do we maximize our score? It's not a trick question. How does Pacman maximize a score from that root node? Yeah.
First, you skip the shortest.
Yeah, right. Or put even more simply, go right twice. The point is that we know, because we have this whole tree, that we can follow any path from root to leaves, and the one we like the most is 8, so we can just go this way. Now we're in this state. Go this way. Now we're in this state. Good. What we're going to add now is the notion of the value of a state, where the value of a state is the maximum ultimate utility we know that we can get from our current state. So of course, if we're at any of these terminal nodes, at any of these places, the value of those states is just that utility. So the value of this is 8, value of whatever's here is 6, etc. But the value here is going to be the maximum score that we can get if we start in this state, which, if we're here, the way we maximize our score is to go right down this branch, which is the max out of our two options. So the value of a state, best achievable outcome, terminal states, VS known. Okay, so for non-terminal states, it's just the max of all the children. And if we propagate this back up the tree, imagine that for simplicity, these are the only utilities that are below all of these states here. If that's the case, then what is the value at this node? Max of all of the future outcomes. 2, right? And then here we have 6, 6, okay? And then now that we have our 6 and 8 right here, we can compute one level farther up in the tree. 8 is what's going to go here, 6 here, 8 here. And so we say the root value of this tree is 8. From our starting position, 8 is the score that we can guarantee to get and is the best score that we can guarantee to get. Okay, so adversarial game trees. What's different now? We have a ghost in the board, and after every one of our turns, the ghost gets a turn. So Pacman can again move left or right, but now it's the ghost's turn. And the ghost can move left or right. If we go down this left branch, then the ghost can either move on top of the pellet or move to the right. Same over here, left or right. And there we go. Now there are a lot more negative utilities because there are a lot more bad outcomes for Pacman. But what's important here is this is just a tree of all the different outcomes. So far we haven't said anything about what is going to happen. This is just a model of what could possibly happen. And everyone's in agreement about this. When I say everyone, I mean Pacman and the ghost agree about what could possibly happen. What they disagree about is what is going to happen, what they are going to choose to do on their respective turns. So we need a similar notion of value that we had on the last slide. But now we can't just take the max of all our children. It doesn't quite work that way because we have these nodes where they're trying to minimize that score. And we get into this idea of a minimax value. And you might be anticipating where this is going. Again, terminal states are just the value. This is part of the game, the way it's defined. We already know these. And every time it's the opponent's turn, right here, rather than maximizing, they take, of all the possible outcomes, the one that is going to minimize my score. So that looks like that. I'll erase that arrow. And then when it's under our control, we're still maximizing, same as before. So remember, zero sum. In reality, the ghosts they also have a score, and they're trying to maximize it. But it's, in this case, the same as just trying to make Pac-Man lose as quickly as possible. So we're modeling it as them minimizing Pac-Man's score. So let's fill in this tree. I want to everyone shout it out. This is the ghost's turn. So what score is there for that node? -8, right. -8 is the value of this node, because if we're searching and we're right here, we know it's the opponent's turn. These are the outcomes. We know the opponent is going to choose -8. So the value, the best achievable utility from that state is -8. What about right here? -10, right? And so from up here, what is Pac-Man going to do? Well, first of all, what's the root value? Louder. -8. Great. So we call that the root value of the tree. That means from where we are right now in the actual game, because remember this is all in simulation, in the actual game, the best achievable score is this root value, -8. And to determine which action to take, well, we just look at our two successors. And which one of those has a higher score? That's this one. And so Pac-Man will take this action. And that's the entire Minimax algorithm, is run the simulation in your head, and then once you get the Minimax values at the children of the root, choose the action that goes toward the highest one. Question in the back. This does assume that your opponent will play optimally, and I have a little note to say about that a bit later at the end of this lecture about what guarantee that actually gives us. Great question. Yeah?
Doesn't Pac-Man lose the most points by moving the furthest without being caught?
Doesn't Pac-Man lose the most points by...
By moving a distance without eating. So wouldn't the worst state for Pac-Man be going all the way to the edge and then getting caught?
Yes. So these utilities are not super realistic for this particular outcome. That's right. And actually, we're going to see in demos where I'm actually running code some examples of Pac-Man will realize that the best he can do is actually to dive bomb the ghost because he's not going to get the pellet anyway. So might as well run down the clock as little as possible. Good point. So here's maybe a more familiar example, Tic-Tac-Toe. How many of you have played Tic-Tac-Toe before? Pretty much everyone. How many of you go home on a Friday night and call up your friends and say, hey, come over, let's play Tic-Tac-Toe? No one. Oh, too bad. I love this game. You didn't keep playing Tic-Tac-Toe for very long after you played it the first couple times. And the reason is the game tree for Tic-Tac-Toe is actually pretty small. Branching factor is the size of that whole board, but the depth, no game is ever going to go longer than 9 moves. And so if you've played it even just a few times, you probably have a pretty good model in your head for what this entire tree looks like. You've solved the game. There's no way to play better than you possibly can. And so if we assign those same utilities that are typical for these kinds of games, negative score for losing, positive for winning, 0 for tie, you know that from a blank board, no matter whose turn it is or who's going first, the Minimax value is 0. You can force a tie. Both players force a tie. Not a very fun game. But notice that I said 0 up there. There's no way that we could end up with some decimal value in our current model up here. It couldn't be, well, min player might make the wrong move, and so it's actually like 0.1, something like that. No, right now the only functions we're using to propagate values up the tree are max and min. So whatever we end up with as a root value up here must be one of these leaf utilities. And you can see we're doing the same thing right here that we were doing with Pacman, where from this state at the top, we expand all of the possible successors for the max player who's placing X's. And then the states could look like this. Now it's the min player who's placing O's. And didn't draw it all the way out, but the same process continues recursively. So let's just take a moment to look at this algorithm and take a step back. So we're solving deterministic zero-sum games. We talked about what zero-sum means, what deterministic means. Tic-Tac-Toe, chess, checkers, Go, Pacman also are all games that fit this specification. One player is maximizing the result, and the other player is also maximizing their own utility, but since that's just the negation of our utility, they're minimizing that same result. And so we have Minimax search in this tree, where we propagate values up from the root until we figure out what the root value is, the best score we can possibly achieve. We can guarantee that we can achieve from here. And then, reminder, to choose an action, it actually matters out of these terminal values what value is going to go in these two nodes right here. Because now from the root, we choose the one that maximizes our score. And that's one more example of those values being propagated up the tree. One of these leaf utilities is always going to end up at the root. We just don't know which one until we actually compute all of this. How would we implement this? Well, at a max node, we need to maximize the value of all the children. So we have this. And there are a few different ways you could implement this, just minor differences in the code. But I've chosen this particular implementation for a reason that we'll see in a minute, an optimization to this algorithm. We start out with value being negative infinity. This is just a starter value so that as soon as we see any value, that's now the best one. We're going to loop through all of the successors and then compute the min value at that successor, because remember we're alternating max and min levels. Once we know the value of that successor, if it's bigger than our current value, replace it. That's now our value. And so we start at negative infinity, and then as we keep exploring alternatives, if we see something better, that's going to improve and improve until we've seen all of the children. And whichever one was the best we saw, that's what we return. And then, of course, min value. Same thing, only now we start at positive infinity. As we iterate over all of the children and find the max value of their successors, that's going to get better and better for the min player as we bring it down and down until it's seen all of the successors and we return whatever the lowest thing, the lowest score of any of the successors, because that is the best score for the min player. And these are mutually recursive. They call each other. This is, of course, pseudocode. What's the important thing that's missing from this pseudocode? Think recursion. Yeah, in the back. Something to start it. Okay, good point. Yes, something to start it, and right here.
Base case.
And a base case, exactly. So you are going to need both of those things when you're implementing it in code, is something to make the initial call to whichever one of these functions, depending on who's going first. And then a base case to catch what happens when we get to the bottom of the tree. Now, of course, if we're at the bottom of the tree, we already know the leaf utilities, so you can just return the leaf utility. And that's how we put these equations that we saw on that diagram into code, where for a max player, the value at this state is the maximum of the values at all the successors. And then at a min node, the value of this state is the minimum of the value of all the successors. This is a slightly different implementation where I'm only showing this because having this in mind will help with the project a little bit. Instead of having it inherently part of the algorithm that min and max are switching layers, you can also implement it with a brain at the middle, basically. And this is actually an example of how you would have something that starts the calls, where the value at a state is going to be either the max value or the min value. And in this function, you determine whether you go max or min. So we draw those same things down there. Value is now just going to call max value or min value. The only real difference here, in terms of why this is more useful, is like I said, in Pacman, we have a bunch of ghosts. We might have 4 different ghosts, and so it's going to be 1 maximizing layer and then 4 minimizing layers in a row. So as an implementation detail, if you do it this way, it's a little bit easier to vary the turn order. Let's see an example. of Minimax. I think we can all, grab the minimum values and put it here, grab the maximum values and put it here. So we're going to run through this instead of from bottom to top, the way that we as humans kind of think about solving this problem, in the order that it's going to be executed by a program that's actually implemented this search. Remember that this is recursive, so we start at the root and recurse down. This is actually going to go through in a depth-first order and slowly build up the tree like we were doing with depth-first search. So at the root node, we're looping through successors. First we see is this one. We need to compute the value at this successor, so we recurse. And now we need to loop through this node's successors. We see this. This is a base case. This is a leaf in the tree. So we just return the terminal utility, 3. Now this is a minimizing player. So now v has gone down from infinity to 3. 3 is the best thing min has seen so far. Then we see 12. Well, 3 is lower, so that doesn't change min's current best option. It's still 3. Still 3 because we have 8. And now we can return a 3 right here and back up at this level in the recursion stack. We're looping through the root's children, and now we go to its second child. From here, recursively compute the value, and we're going to loop through children again, this time minimizing. And we have 2, so now the best it's seen is 2. 4, best it's seen is still 2. 6, still 2. So this one returns 2. And what's happening up here in this level of the recursion stack? Well, remember, this is looping through its children, and it's a max node. So it started at minus infinity. And when the max first saw this 3 right here, v up here got set to 3. So max currently sees 3 and is continuing the search to see if it will find anything that's higher, that's better for it than 3. And it has one more child to search. So we'll go this way. Same story, we recurse. 14, best the min's seen so far. 5, that's even better. So now the min value temporarily is 5 until we finish searching. 2. Okay, so 2 is the best value it saw. Now that loop where we went over all of the max node's children right here is finished, and we return the best value that was computed in that loop, which is 3. So now we end up returning 3 up here. And of course, which action are we going to return? Since we're actually trying to do something, choose an action is our ultimate goal here. We're going to choose the action that goes this way. And when we're talking about tic-tac-toe chess, any concrete game, there's usually going to be some way of identifying that action. Like in the case of tic-tac-toe, that would be put your X in the middle square, something like that. Well, actually in tic-tac-toe, it's 0 everywhere. But supposing tic-tac-toe were harder, and you could actually make a difference by playing well. Yeah, so that's what Minimax looks like from the perspective of the code that's actually running it. And keeping that in mind will help when you're debugging your project, that you're proceeding in a recursion stack in a depth-first order through the tree. We think of it as, here's our entire tree, propagate values up. The way we compute it is depth-first search, more or less. So let's talk about the efficiency of this algorithm. How efficient is it? Well, it does have to go through that entire tree. We have to go to every single leaf utility to determine which one is going to be chosen by the alternating sequence of moves from me and my opponent. So it's the same runtime as DFS, exhaustive DFS, where we're going to go through the entire tree. If B is the branching factor, number of moves at any turn, and M is the depth, total number of moves in a game, then runtime is B to the M. And then your space complexity, since you're just keeping track of that recursion stack and all the local variables attached to each one of those, it's basically the same as DFS there as well. O of Bm, B times M. Now, Bm, we don't really care about that. That seems pretty small, that's okay. B raised to the M, that's exponential in the depth of the tree, in the length of the game, number of moves in the game. How many moves are there in a typical game of chess? Well, you can get up to 100 in reasonable games. So we're talking about 35 raised to the 100th power. No way we will get there anytime soon. So exactly computing the minimax value according to this algorithm we've seen so far, not really feasible. We're going to talk about improvements in a second. But first, I want to talk about what happens when you're running Minimax under the assumption that your opponent is going to play optimally, and that assumption is not always right. So actually, let's fill in that tree real quick. So if we're looking here, that's a min player. Both of its options are the same, so it's going to be 10 in that node. And over here, of course, since it's minimizing, let me use a different color. 10 there. And since it's minimizing, it's going to be 9 there. And max is going to choose the max of those two, go to the left. So even though there's that 100 leaf at the bottom, since it's assuming that the adversary is going to play perfectly, it knows that it can't reach that, so don't even bother trying to go that way. If you've played Go or chess or any of these kinds of games really extensively, this is probably a kind of reasoning that you've gotten used to, where we assume the best of the opponent so that we can guarantee a certain outcome. But sometimes this isn't always a perfect assumption. So let's first see Pacman playing. Oh, let me move that demo out of the way. Pacman playing Minimax right here, so assuming the best of the opponent. This is like what we were talking about before, where it knows that the blue ghost is not going to move out of the way so it can collect those dots. So it's going to die no matter what. It loses points for every time the turn count ticks. So what's the best thing it can do? Move to the right. Try to die as quickly as possible. So let's see that. Okay. He just ran Minimax search, killed himself immediately. No surprises. But suppose we actually had ghosts that were not perfect adversaries. They were not choosing the best move out of their options, but just moving randomly. Well, now what? Now there's a possibility that that blue ghost, if it's choosing randomly out of moving up or down, is actually going to go down the other direction. And if it does that, then Pacman can make it to all of those dots. There's still the possibility that it'll move up, and Pacman will get still stuck and be alive for one more turn, and so end up with one less point than if he had gone right. But the prospect of being able to get those dots makes it worth it. So first thing, this is actually random, so we might not see what we want the first time. Oh, there we go. He moved out of the way. So now Pacman's really happy. He can get all of the dots. There we go. Okay, so what we're seeing is a scenario where the sort of pessimistic assumption that your opponent is going to make whatever move is as bad for you as possible is not, self-evident. You have to actually have some reason to believe this for it to be the best model you can choose. We'll talk tomorrow about how to reason in a similar way, but where there's some probability distribution over your opponent's moves rather than, they're just going to choose the worst every time. But keep that in mind. And there were a couple questions about that already, where sometimes you could do better if you took a chance. If you assume the best of the other player, then Minimax is the algorithm. Sorry, I'm pulling up the slide again. So in that first demo, we saw Pacman playing against this Omega robot that knows everything and knows that you have to put an X in front of the O's so that he can't finish his 3 in a row. And in that second demo, he was playing against this guy who doesn't really know how to play the game so well. He may have just kind of chosen a random move. That seems pretty good. He set up, now next turn there are 2 different ways that he can win. No. Anyway, point is, there are other ways of reasoning about this. We'll see them tomorrow, but this is not the end-all be-all algorithm. So let's talk about resource limits. We already said that in realistic games, we can't search to the leaves. And more specifically, what I said was in chess, as an example, 35 to the 100, that's the runtime it would take to exhaustively solve the entire game in that way. We can't do that. And in most real-world problems, they're too big for us to do that. So The solution is depth-limited search. Depth-limited just means now rather than searching until we get to a terminal utility, we have a new base case, which is if we've now searched through 8 plies in the tree, and just quick vocab note, a ply is a sequence of everyone taking their turn. So 1 ply in a 2-player game is each person takes 1 move. After we've searched 8 plies, then just estimate the cost to get from here to the end. And of course, how do we estimate it? That's a difficult problem and a problem you will face on Project 2. It's going to feel similar to designing heuristics. It's a similar kind of concept. But the key idea is now we have to actually encode some human knowledge how to estimate what states are good and what states are bad. So in the tree, this looks like this. If that were the entire search tree, in this case, we just searched 1 ply. You know, max player had 1 turn, min player had 1 turn. But we got to that second row, and rather than continuing to simulate what the other players would do, stop, apply our evaluation function, that's what we're going to call it, and then just treat those as though they are the terminal utilities. So, as an example, if we have 100 seconds, can explore 10,000 nodes per second, that's not actually that much, but just for easy numbers, we can check 1 million nodes per move. Then in chess, alpha beta, which is another tweak to this algorithm we'll see later in this lecture, we can get to about depth 8, which, you know, that's not depth 100. We haven't solved the game perfectly, but that's pretty decent. If you can look 8 moves into the future and say, of all of the outcomes, I can see in 8 moves which one is going to be the best, at least according to some sense of what I think good boards look like. That's the evaluation function. Now, we lose some stuff when we do this. The guarantee of optimal play is the main thing, where with exhaustive minimax, we actually have a guarantee, because we had the root value, and the definition of that value is the highest score we can guarantee, that we'll be able to do at least this well. Now, if we're just approximating, then we're vulnerable to whatever error there is in our estimate of what the value is from a certain node. And so it could be that right here, oh, bad choice, that's actually a terminal node. Right here, that 9 is a terrible estimate. It's actually, if we end up down here, 4, 4, I don't know, something much lower. And so, how about negative 100, just to make the point even more clear. Negative 100, negative 100. This 9 was a pretty bad estimate, but it's part of the reason that the max player chose to go this way. That's a kind of scenario where if your estimate's bad, you will do far below optimal play. But more plays makes a big difference, because in general, the reason that we have this error in our guess as to what the terminal utility will be is because it's so far in the future. If we take more steps in our search, we get closer to that, and so it's easier to make this estimate more accurate. It's kind of like if you're trying to estimate how good a chessboard is, and everyone has, well, you have 3 pawns and a king, and the opponent just has a king, you're kind of in the end game. It's really easy to see that you're in a pretty good position. Whereas at the beginning of the game, if you are 1 or 2 pawns ahead, it's hard to really know at that point how much of a difference that's going to make. Yeah, question?
So for optimality, does this whole thing fall apart if the players are playing simultaneously? Because you can't tell what the other guy does, so you would respond optimally to what they do.
Yeah, good question. How does this work for simultaneous games, where they're taking turns simultaneously? We don't use this kind of algorithm for that. This is an algorithm specifically for turn-taking games like this. Now, you can kind of mess with your model sometimes for a lot of problems, where Pacman is a game where if you go and play it on an arcade machine, then you're kind of moving simultaneously with the ghosts, but we can reasonably model it as they're taking turns, where after you've taken a move, you see what the ghost did. And they may not have done that, explicitly speaking, in response to your move, but now you can respond to that. It kind of depends on the way you're modeling it.
So you're saying it's kind of a weak model when it comes to Pacman?
Well, so the question is it a weak model for Pacman? The Pacman code that you're working with in your projects actually is turn-based, so it's a perfect model for that. But yeah, sometimes the model doesn't work out so well for simultaneous games like actual Pacman. Other question?
Isn't it possible to lose the best checkmate because the heuristic was so extreme against a set of moves?
Yeah, you can lose all sorts of good outcomes if your heuristic evaluation function, as we are going to call it in this context, is not a good estimate. If it's really, really low, when in reality you may have just lost your queen, but it set up a checkmate one move later, then you're not going to see that unless you search one move deeper in the tree. Okay. And that's that. More plasma makes a big difference. Quick nod to this other algorithm. In practice, this is how it's usually implemented, where if you're doing iterative deepening, first search at depth 1, return a move, or rather have that move on hand, and if we run out of time, return that move. Then do the search again to depth 2, and whatever move you learn from that, that's now your best move. And you keep going. You're kind of iteratively improving which move you think is good. And the reason this is useful in practice is because, you know, chess engines, they have time limits on their moves, and you can say, always search to exactly this depth because you know that you're never going to run over the time limit. Or you could say, every single time, there are going to be some variations based on all sorts of things. Let's just compute to the end of the time I have, and then whatever the best thing I've thought of in that time is, that's what I'll return. And that property is anytime. An anytime algorithm is one where at any time it can return some answer that'll get better the more time you give it to compute. So like I said, depth matters. The evaluation functions are always imperfect, and the deeper in the tree it's buried, the less that imperfection matters, because more of the behavior is going to arise from just that ability to see into the future, and less of it is going to be coming from how good your evaluation function is. If your evaluation for Pacman is just, am I close to a dot? Well, when you start out, that's going to be, yes, I'm close to a dot. Every single turn doesn't tell you that much. But when you're at the bottom of the tree, that really tells you what you want to know about what's left in the game. And similarly to search, when we were talking about heuristics that are expensive to compute, if you have an expensive heuristic, then you'll have to compute fewer nodes, but it takes more time to do that. Similarly here, if you have an expensive evaluation function, then it's going to be generally a better estimate of the actual value, but you're going to spend more of your time computing those than actually going deeper in the tree. That's another one of those trade-offs you'll work with a lot in Project 2. So I want to show a demo of an example where the depth makes a huge difference. First thing we have is Pacman in this situation, and he's searching at depth 2. So truncating the search at depth 2 and then applying an evaluation function to determine what's best. A pretty reasonable evaluation function here is how close to that dot am I, because his goal is to get to there. So he's going to run that search. Oh, nope, go away. Run that search, and what's he going to do? He has two options, up or down. Raise your hand for up. Raise your hand for down. All right, great, yeah. He's going to go down because, of course, that's what's going to maximize his evaluation function, is getting closer to that dot. And now he has to go one of those directions. Of course, for the same reason, he's not going to go up. But the blue ghost has a chance to react to the choice he made, and now he's trapped. And he doesn't know what to do. He gets caught. So that was depth 2. And here's what it looks like if we can search all the way to the bottom of the tree. And this is feasible for such a small game. This is Mastermind Pacman again. So he knows everything that will ever happen. We're going to see some weird behavior because any reasonable evaluation function is going to say, this is a totally crazy move. Why would you do that? You've moved farther away from the dot and closer to the ghost. But in fact, Pacman can see that as a result of that choice, he's still not really in any danger because he's moving before the ghost. And once he gets here, he's forced the blue ghost to commit to a direction, and now he can go around this way. And he actually gets it. So we didn't make the evaluation function any fancier. We just said, search deeper in the tree, and then Pacman is much more able to catch on to these strategies that in the short term look crazy. You lose something in the short term, but in the long term end up better. Okay, so now we need to talk about evaluation functions. How do we actually come up with these? Well, let's look at an example for chess. And not a full example, just kind of an example of the thought process. So the ideal function, again, since we're trying to estimate the cost, would be just to return that cost. Of course, we don't know that, so in practice, what we're usually going to do is come up with a bunch of measures of things about the board, information that might be relevant, which this is a pretty good example for chess is queen advantage. All that means is if we're playing the white player, then we want to know, do we have more queens left than the opponent? If so, that's pretty good. That's information that is probably relevant to computing the value. So we'll have that. We could have a whole bunch of other things like knight advantage. Same thing, do I have more knights? Then you can have more complex things like, do I have pawns that are farther on the other side? And this can get arbitrarily complicated, but it's just kind of logging a bunch of this kind of information about the board, and then figuring out weights on each one of these. So of course, having queen advantage, if we're white, this is going to be a positive number, and if we're doing well, we want it to approximate a positive score. So if that's F1, then W1 is probably going to be some big positive number. And then if F2 is knight advantage, which means how many more knights do we have than the opponent, that's good, not as good. So W2 will probably still be positive, but not quite as big as W1 because it doesn't make as big a difference. And then we might have some other F that could be like Fn equals how close is king to center. And if you've played chess a lot, you know having your king out in the middle, usually bad. There are exceptions, but you want to have your king back here protected well in most cases. And so to a first approximation, this could be something where Wn is actually negative. The bigger this is, the worse we're doing. And so this is what the process of coming up with these for your project is going to feel like, is you figure out all the relevant information about the game. It's like, how close am I to a power pellet? How close am I to the nearest food? How much food is left? What's the game's score? All these things about Pacman. And then you're probably going to do some experimenting to figure out what good settings for all of these linear weights are. Now, when we get into machine learning later in the course, you'll see more sophisticated ways than just humans going in and trying to figure out what to do with that. But for now, that's what we're doing, is log information into these functions and then combine them in some way. It doesn't have to be linear in this way either, but this usually works pretty well and has some nice properties we'll see later. Much later, actually, when we get to machine learning. So, yeah, imagine we have this eval function. Just quick note about what that's going to do here. We could just as well apply the eval function at the root, which that's what this is. See, it's pointing to this root node here. We're searching from that position, trying to decide what the best move is. If we say, run the evaluation function on each of my successors and then choose which one's best, what kind of agent is that? Quiz going back to the second lecture. Yeah. What was that? Greedy, yeah. It's a reflex agent that is greedy because it's just greedily trying to maximize this eval. And another phrase we recently learned to describe this behavior, this is a hill climbing algorithm where this is our objective function. So that's kind of the limit going towards 0 of depth. What this algorithm becomes is just hill climbing. And then on the other hand, we can actually search to some depth and do it. And generally that will perform quite a bit better. So let's talk about evaluation for Pacman. Now, a first easy choice for an evaluation function, if we're just trying to make Pacman maximize a score as much as possible, is what is Pacman's current score? So that just means if you're searching to depth 3, then after 3 moves, choose the branch that has maximized Pacman's score at that point. And then presumably that's the same branch that's going to maximize Pacman's ultimate score at the end of the game. So let's see what happens. This is Pacman searching at depth 3 with that evaluation function, where he's just trying to maximize his score. And remember, it goes down 1 every time step and up 10 every time he eats a food pellet. So of course, he goes right. Now what's going to happen? Down. We would expect down. Something weird's going to happen. He moved left. Why did this happen? What's he doing? We're starting to kind of lose faith in Pacman's choices here. You may be thinking, oh, maybe this isn't a great algorithm after all. So this is actually a danger of replanning agents, and this is kind of a flaw in that particular choice of evaluation function. So let me show you why Pacman starves. Oh, we'll come back to this slide in a second. So the danger of replanning agents is at the root, again, same as always, 2 options evaluating whether he should go left or right. If he did that, or if he does those 2 options, these are the outcomes. And if we were just searching to this depth 1, and this is not really a minimax tree because there are no min players, but if we just apply max at every layer, it's more or less the same algorithm. If we're just going to depth 1, then the choice is clear, right? This is going to, oops. Well, the left choice is going to have score 9. It went up 10 and down 1 because we passed 1 time step. And this choice is going to have -1 because we didn't need any food. But we're searching to depth 3. Actually, in this case, we're doing 2. So only 1 successor there, and those successors there. So now we're terminating here. What are the values of these nodes? Well, here we got a dot, and so we got 10 points, and 2 time steps have passed. So 8. Over here, we didn't need anything, -2. And over here, we also got a dot, and 2 time steps have passed, so 8. What's the problem now? Well, Pacman's going to be indifferent between these 2 outcomes, right? Because they have the exact same evaluation function. And so if your tie-breaking order is as bad as it can possibly be, which in a lot of cases it's going to turn out that way, then Pacman might choose to go this way. And if Pacman goes this way, then now he's running the exact same planning problem at this state. And he's searching at depth 2 from here again. And what does that look like? Well, it's going to look kind of like the same board again, where we have Pacman over here and a dot here, and that has score 7, because 1 more time step passed. And then down here, well, there are 2 outcomes. And he could eat the dot on the left or move back to the middle. And from the perspective right here, it's going to be indifferent in exactly the same way between going toward the farther food or the nearer food. And so it could choose to thrash back and forth between those options, where from here, this looks just as good as the alternative, and then from here, this looks just as good as the alternative. In the demo we just saw, let me pull that up again. Yeah, so in this demo, here we're searching at depth 3. So Pacman's here, and he can either go down and then do some stuff, and he'll have eaten that dot, and 3 time steps have passed, 7 points. Or he could go left, come back, and then go down. 3 time steps have passed, 7 points. It's all the same to Pacman, and so he chooses to go left, and then we already saw what happens. It's pretty tragic. So how can we fix this? Well, let's look back at that slide. We have these outcomes down here, and we're talking about the leftmost one and the rightmost one. The score is the same, but which one of these is actually better? The left one, right. So this one right here is going to be better. And why is that? He's closer to the dot, right. So from here, it's going to take less time for Pacman to get here over to the other dot. He's only going to lose 2 more points before he gets it. Whereas over here, he has to take 3 time steps to get over there. So in terms of actually estimating the ultimate score at the end of the game, it would probably be helpful to us to account for the fact that this is better than this. So what if we add a partial credit bonus, where rather than the score that he's going to have right now, you also say, plus, half of that for how close you are to the next dot, or something like that. Then this is going to kind of edge that out a little bit, where this was 8, maybe now it's 8.5, and we still have 8 over here. Then now Pacman's going to go to this direction. And if we want to see, now the evaluation function has been changed so that it's the score plus a bonus for being close to the next dot. He does the right thing. The point I want you to get out of this is you're going to be implementing all of this pretty soon. Implementing Minimax is really just following pseudocode. It's generally, you'll have some debugging to do, but you'll get it to work. When you actually observe poor behavior from your agents, most of the time it's not going to be a bug in your search code, just like with heuristics. Having a bad heuristic leads to bad behavior. Here, in even more subtle ways, there are pretty serious consequences for the design choices we make about how this evaluation function should work. So there's something to keep in mind. If you see thrashing, it's probably something that's a result of this replanning like this, and you want to be able to give Pacman more information. So last thing to talk about today is game tree pruning. So we already said we don't know how to explore the whole tree. It's just way too big. But we'd like to go as deeply as possible, because the deeper we go, the better we perform. The more we can see long-term strategies. So we're going to look at ways to prune the tree. And when I say prune the tree, I mean exactly what this robot's doing. Cut off branches because we don't need to explore them. How can we guarantee that we don't need to explore them? Well, let's look at an example before we try to come up with a general case. So this is the same one from before, where I went from top-down depth first order through the recursion tree. So first, we look at the root's first child, and we loop through its children, 3, 12, 8, and the best option that it got from any of those is 3. Then we go back up here. The best thing that the max node has seen so far is 3, so it's considering that, but it also has to search its other children, because it could still potentially learn that this value at this node right here is going to be something higher than 3. It could be 4, and then that would change what we do at the root. So we have to search this way. We get 2. So now what happens? Remember we had that loop where the min player starts at infinity and then iteratively improves its best option until it's gone through all of its children. Which means already at this step, we know that whatever goes in this slot right here, I just drew that backwards, is going to be less than or equal to 2. Right? Because we've already seen a way that we could get 2, and the only way this value is going to change from 2 is if it goes even lower. So less than or equal to 2. What does that mean for us up here? Well, we already know that we're not going to choose to go that way, because we have a better option than that to go this way. So no matter what we see in these root nodes, or these leaf nodes over here, these could be catastrophically bad utilities, bringing this even lower and lower, but our goal is to compute a move from this root. And so from that point of view, what is the purpose of really figuring out exactly how bad it is to go this way if we already know that's not what we're going to do? So we can just not go this way. Not even bother to look there. No matter what we find there, if it's bigger than 2, then min node won't choose it. And if it's less than 2, then the min node will choose it. But we already know we're not going to go that way anyway. So this animation is actually going to show them, but yeah, that's how we know we actually don't have to keep searching in that direction. So from the perspective of the top, it's still possible that we could have something here bigger than 3, so we keep searching. And we see 14. So now we know this is going to be less than or equal to 14. But it's still possible for something to be less than or equal to 14 and bigger than 3, which means if we see something here that's in that range, that's actually still going to change the outcome of the search. So we need to keep searching. we see 5. That's much better for the min player who is making the decision at this point. So rather than less than or equal to 14, we have less than or equal to 5. Still possible that we could find something else over here like 4, and then we would want to go this way. And we could find something like 2, which would mean we want to go this way. Want to go this way. Point is, it still depends. What move we choose as the root still depends on what we find here. So we have to keep searching. And we see a 2. So now this returns a 2, and we go this way. We already saw this example, so we knew that was what was going to happen. But key thing, we didn't really care what we found there. This is why it still animated it. I had another slide that didn't animate it. Whoops. Okay. So yeah, same thing again. We can jump past this. Alpha beta pruning. So this is the algorithm that is what we can take away from that. And the idea is we're going to look at this from min's perspective. So computing a value right here. What I mean by that is we're still assuming that max is trying to choose a move at the root, but we're computing the min value at this node right here. So we're looping over n's children, and n is starting at infinity, and every time it evaluates a child, it's going to see if that improves its current best choice. So n's estimate of the children's min is constantly dropping, or at least staying the same. It's never going to go up. So who cares about n's value right here? N's value right here, who cares about that? This max node right here. And in particular, the max player, who controls which way we go at every max node, every blue up triangle. That's who cares what the outcome is there. And so what we need to consider is what other options does max have? So this is somewhere up in the tree from where we're currently searching, way up here. We're searching what would have happened, or what will happen rather, if blue chooses to go down this branch. Take this action and then some sequence of stuff that gets us all the way down to here. But way back up here, there was somewhere where we had a different option that could have gotten us a value of A. So the idea is, if A is a better option than N, then we would just go with A instead. There's no reason to keep searching this way. So remember, N is continually getting lower and lower. So rather than finishing the search, and remember, each one of those children you evaluate could be pretty expensive because it could be a recursive computation to go much further in the tree. Rather than finish looping through all of the children, the moment that this value of N gets less than A up here, which is something max already has access to, then we know this branch couldn't be better for us than N, and we already have something that's better than N. So why even bother continuing searching? We know we're not going to go that way. So that's the alpha beta algorithm, the reasoning behind it. We'll see pseudocode in a second. I want to walk through one other way you could conceptualize this, which is in order for us to care about a value in this tree, it would have to be the case that that value changes the move we take at the root. And in order for that to happen, that value would have to get propagated all the way back up. So it's not building up the tree this time, but we're going to say we're searching from the top, go down all the way to the bottom, and then, so this is the first terminal state that we get to, the first leaf in the tree. Evaluate it. 3. Okay, well, there's not much we can do yet here. There's no kind of guarantee that we get from that, because this could be, 100, and then that would change the value here. And anyway, there exists some configuration of the rest of the tree where what we have here actually could get to the root node. So we have to search that as well. And then out of those, this is a max player, or I'll use blue for that. So it's going to grab that 4. And then we recurse down this branch, and we need to look at these leaves again. If this is something, if these are both something really big, this is going to be high, this is going to be high, and we'll choose it up here. So it still matters. we'll search there. But now we kind of have a situation where we know that this min player up here can guarantee that you get less than or equal to 4. And this max player can guarantee that you get greater than or equal to 5, right? So if this is something that the max player right here will choose, then it would have to be bigger than 5, and that means it's not going to get chosen here. In other words, in order for this value to get propagated all the way back up to the root, it has to satisfy both of these conditions, greater than or equal to 5 and less than or equal to 4. But there's nothing that lies in that interval. If we'd had a different value right here, so that this was like a 6, then instead of less than or equal to 4, it'd be less than or equal to 6, and we could find a 5.5 right here. There would exist something that satisfies both of these conditions, and so we'd care about what's there. But as it turns out, we are here, so there's just no possible value that could be the root value here. Don't even bother. We get that. Now, in order for something over here to get passed up, well, it would have to be bigger than 4 because we know that this max node can now guarantee that it will get something bigger than 4. It's seen this option, but there are no other restrictions on it so far. So we actually do have to check that. 2, and then same here, it would have to be bigger than 4. If that were the case, then it would be possible for it to go up to the top. So we have to search there. And then we get a 2 here, and a less than or equal to 2 here. Remember, this is like min is looping through. It started at infinity and keeps going down. It's seen a 2. So this will be less than or equal to 2. And then now we're at this level right here and considering this other branch. So it doesn't just have to be at the leaves. Even at this recursive step, in order for something that would be returned by our recursive call right here to go up to the top, this node would have to choose it right here. So it'd have to be less than or equal to 2. And this node would have to choose it. So it'd have to be greater than or equal to 4. Impossible. So nothing that could be in this node could be returned at the root. We don't even need to bother searching. So on that previous slide, we walked through one way of thinking about it. The punchline for this one is a root value would have to be able to propagate all the way to the top. And so it would have to be chosen by every max node and every min node along that path. How would we implement this? Well, same pseudocode as before, where we have our mutually recursive functions. And remember, you can also have that dispatch that helps a little bit, especially on the project. But now we've added some stuff to the loops in here. We initialize them exactly the same way, only now we have these two values, alpha and beta, that correspond to alpha is the best thing that Max has seen along any alternate path down this path. So any Max higher up in the tree, options it's seen so far, the best out of all those is alpha. We know that since that Max, all the Maxes, but in particular that one, would have to choose this branch over any others, whatever we find now has to be bigger than alpha. So that's why we're keeping track of that. And then over on the other side we have beta, which is the same thing. Any min node up higher in the tree, it would have to be lower than that for that min node to, lower than the best thing that min node has seen, in other words the lowest thing, in order for that min node to choose it. So we have these two bounds, alpha, which is as good as the max can do, and beta, which is as good as the min can do. And any value that could go up to the root has to be between those, in that interval. And so our short circuiting is as soon as those values cross each other, as soon as that interval becomes empty, we can stop. There's just no reason to keep searching. We're not going to find anything that's going to become the root value. And so minor implementation detail, you can come back and look at these when you're doing the project. But if we see a new V that's better than anything we've seen before, that's going to be the new alpha. And so we can just check if the V we just saw is bigger than alpha, rather than checking if alpha is. minor difference between what I just said and what's on the slide. Not a super big deal. And same thing over here for min. So sorry, I'm going to go just like 1 minute over because this is really important, that alpha beta pruning, if you follow that reasoning, you're actually never going to terminate a branch of search in any way that can change the root value. But the values of the intermediate nodes might be wrong. We saw that example where I just stopped at less than or equal to 2 instead of continuing to search and seeing that there could be other things that are there. If we had run into a negative billion there, that should actually be the value at that intermediate node, not 2, but it doesn't change the action we return. Another kind of minor implementation detail, but that comes up quite a lot, is that if anything except the root has the wrong value, in particular we can have children of the root, where this first level down right here, values here is actually what gives us the action we choose. If these are wrong, the most naive version might confuse us, because we can see, if you go through this, I'll just hurry through, you'll see that alpha beta lets us prune this, and then we return 10 here and here, and max is indifferent between those options. So you want to be a little careful about how you implement alpha beta. Either come up with a way to tie break that always goes the safer route, or only start pruning after the first level down. Either of those different fixes to this will eliminate this bug. Good child ordering improves effectiveness of pruning. You saw in that example I walked through, in the middle branch we had a 2 that was at the left of all of the children, and we saw it first, so we knew we didn't have to look at the other ones. And on the rightmost branch there was a 2 that was all the way to the right, so we had to look through all of them in order. That more generally applies in all cases where the order that these things are arranged in the tree is going to make a pretty big difference. We're not going to talk much in this class because it's pretty complicated about how to order those, but a lot of actual implementations like chess engines do a lot to try to keep those in the right order. And with perfect ordering, which is, for min player, the minimum thing is always first. We can't actually guarantee this, but if we could do this, then the time complexity drops. You get a factor of 2 away in the exponent. In other words, we square root it, and thus we can go to twice as much depth. Now we're looking at depth 16 for those same hardware limitations for chess. Way better. So that's what you want to know about alpha beta. You'll probably need to come back to these slides before implementing it or look at the pseudocode, because there are some complicated little points there. But that's everything that you should be thinking about right now. Thank you.